In this video, I'm going to be showing you how to expand multinomials. Many of us know the binomial expansion formula. This works for when the inside of the sum only has two elements. It is necessary in a computer algebra system to be able to do this for more than just two elements in the base of the exponent. Maybe there's 7. We definitely don't want to expand the entire product out and FOIL it out completely. That's very slow. First, I want to look at being able to get the coefficient if we are given some term. So for example, if we had a plus b plus c plus d to the 12, we know that there's going to be a term in there of a times b to the 7 times c squared times d squared, but we want to know the coefficient of this term. First, I want to show you a seemingly unrelated problem. How many ways can we rearrange the word q? Like in distinguishable ways. In the word Q, there's one letter Q, 2 letter U's, and 2 letter E's. So to find the number of ways to arrange this, first let's place the Q. It has 5 places to choose from. In other words, there's 5 choose 1 possible ways to place the Q. Now we have 4 spaces remaining, and we're going to place 2 letter U's. So 4 choose 2. And finally, we have 2 spaces left, and we have to place 2 E's. So that's 2 choose 2. Multiplying this all out, we get 30 ways. So there's 30 ways to rearrange the word Q. Now finding the coefficient is the same kind of problem. If you see, we expand out a plus b plus c 4 times. Expanding this is finding all the possible ways to combine the letters. However, some of these groups of letters are really the same thing. For example, a times b times b times c is the same thing as b times a times b times c. And to find the number of ways that these terms add together, it's really just counting the number of ways you can rearrange those letters. So now looking at the product again, a to the 1 times b to the 7 times c squared times d squared, we now know how to get the coefficient. We have one letter a, and we have 12 spaces to choose from, so 12 choose 1. We've used 1 space, so now we have 11 spaces left. And there are 7 letter B's, so 11 choose 7. Next, we have 4 slots available. And there's 2 letter C's, so 4 choose 2. And lastly, we have the 2 slots left, and there's 2 D's, so 2 choose 2. Multiplying all these together, we get 23,760. That's the coefficient. I've made an example algorithm in Python 3 where you give it a list of the exponents and then the actual exponent, and then it will calculate the coefficient. Next, we're going to be moving on to how to calculate all the possible exponents. So for a binomial, if you expand it out, the powers basically switch from the one to the other variable. So if we do a plus b to the 4, you have something times a to the 4 times b to the 0, and then each term a gets smaller by 1 and b increases by 1. But those exponents always add up to 4. So if we generalize this for if we had 3 variables, then it would be all the possible ways we can add up to 4 with 3 numbers. And those are all the possible exponents for the trinomial expansion. I've made a table with all the possible ways, and I would just look at it and try to figure out the pattern. I'll show you a recursive algorithm to generate this next. So this algorithm will generate a list of lists where each element in that list is the possible ways to add up to that number. It's recursive. It's like a nested for loop, but in a recursive kind of way. And then for the last number, or the base case, you're trying to find the number that you need to add to finish the sum. It's a little bit hard to understand, but if you try to come up with your own algorithm that fits the data from the table on the previous slide, I think it'll make sense. So here's an entire program with all the elements from the previous slides that expands a trinomial to the power of 4. And the output generates a bunch of sublists where the first number is the coefficient, and then it shows you the set of the exponents. So if you look at the table, it would be 1 times a to the 0 times b to the 0 times c to the 4 plus 4 times a to the 0 times b times c to the power of 3 plus 6, and so on and so forth. This is definitely a lot better than trying to FOIL this out or recursively, doing a product inwards and inwards and then adding all the terms together. Multinomial expansions can be useful when you're doing integration, because sometimes you have some polynomial in some funky kind of form, so expanding it just makes it a lot easier.